graded materials, carbon nanotubes, and reinforced composite structures, periodic structures such as hexagonal lattices, sandwich structures, fluids, and electromagnetics. He has successfully solved many of these wave propagation problems through a unique combination of sound mathematical skills coupled with innovative and original ideas. His notable contribution is the invention of a new numerical method called spectral finite element method, which has already become a tool to solve many wave propagation problems in complex media. Thank you, sir, for giving us your valuable time and enlightening our audience with your knowledge on non-destructive testing and evaluation. Thank you, sir. Kindly start, sir.
Thank you, Sheikh Nazir, and I'll just try to share my presentation first.
We have three minutes, huh? 5 minutes, 7 minutes. Okay, look, no problem.
No problem.
11 minutes, 10 minutes to 11. As per Air Force rule or Army rule, 11 means does not means 11. 11 means 10 minutes to 10.
Here we mean.
Are you able to see my slides?
Sir, yes, it's presenting, sir.
Yeah, okay. So good morning, all of you, and I thank the NIT Srinagar, Sheikh Wazir, and others for inviting me. I've been working in this area of health monitoring for quite some time. We have made several contributions in this area, my group here at IASC. I'm going to talk about one small aspect of health monitoring that is, which is very important, which is important both from NDT perspective as well as health monitoring is the sensor technology. So let me go through the presentation now, and you can interrupt me whenever you want if you have any questions in this regard. So my talk outline is going to be this way. So I'm going to basically introduce SHM, that is health monitoring, and what it is and what are the important aerospace applications in India we do here. Then I'm going to talk about what are the conventional sensors in SHM, what are the people use, what are the current design practices in SHM, and then I will shift gears and I will talk about two important contributions that IASC has made in the area of sensors for SHM. One is the magnetostrictive sensors, where I will discuss a little bit about the theoretical formulation and some of the experiments that we have done. And we will show how we could actually monitor on small structures on magnetostrictive. And then I will move to a very important area on health monitoring, that is the LDV technique, laser Doppler vibrometer technique, where I will talk about its usage, how it could use, and we will show some of the real-time applications in aircraft that we have made in a bigger fighter aircrafts in US, where we actually did the testing, and some of the conclusions I'm going to make. So let me go to the introduction. What is SHM? The SHM is basically a study involving monitoring, detection, arrest of the growth of flaws, such as cracks or delaminations. That is one part. And then finding the residual life of the structure. Because you would have designed a structure for certain life, but because of cracks, the life will go down. How will you calculate? And finally, these two combinations is constitute what is called the health monitoring. So on the left side, I have a flow chart here, which says that the structural health monitoring has two components. One is diagnostics. The diagnostics is basically to say where do you have flaws, and the prognostics is how much of life that is left because of these flaws. Because you would have designed it originally for certain amount of life, but that life gets down. That is what is the prognostics. And the diagnostics and prognostics together will form one component of IVHM. IVHM stands for Integrated Vehicle Health Monitoring. But in aerospace, the diagnostic still has two more components, which is not there in other areas of structures, in mechanical structures. That is offline health monitoring and online health monitoring. Online is, as the aircraft flies, if there is a flaw, it should be able to monitor and tell immediately that something is happening. That is still not on, in spite of tremendous amount of research that's been taking place in this area. But substantial progress has been made in offline. So what is offline? Offline is when the aircraft has flown and it comes to the hangar, you do certain methodologies to find out what is there. And this is very, very important, especially in the context of maintenance of the aircraft. I'll come there, why we need this. Online health monitoring is still far off. There is no online health monitoring that is in place in any of these aircraft, because still the reliability of these systems, the sensors, have to be still established. They are working on it. Maybe in all our lifetime it will come. But offline health monitoring is very much there, and many of these airlines are now using it. So what is SHM? For people who doesn't know, SHM is some kind of monitoring. It's like a structural doctor. If you really missed out, you wanted to be a doctor and you couldn't be, and you became an engineer, this is a chance for you to become a doctor. So what is the similarities between the two? So when you get sick, you go to the doctor, monitors patients, uses some medical equipment like stethoscopes to find out what is there, your heart rate, your pulse rate, and based on it, he will prescribe some corrective medicines. So let us bring this analogy to health monitoring. So we need to monitor the condition of structures. And how do we do it? We need sensors. Just like the doctors have equipment, simple equipment like stethoscope or few other equipments, like testing ultrasonics, everything. We use sensors to check the overall health. And some of the sensors could be common. For example, ultrasonics is used both in medical as well as in SHM. And if there is excessive stress or deformation, because of which the cracks will form, we will prescribe some corrective actions and do some repairs if possible, or change the structure, change the monitoring condition, change the stiffness of the structure, do whatever to actually see that the structure is safe through its life. So why do we need SHM? When did this all started? So essentially, if you look at it, they started way back in 1969 when in the Wright-Patterson aircraft base in US, they had a problem where the left wing was lost at the low training flight. And when they examined it, they found that there was a flaw in the left wing of the size 1 into 0.2 inch, which was undetected during their NDE examination. And because of that, the left wing was lost. And that time, the Air Force mandated that they introduced a new MIL class that is standard that says that you need to have a monitoring system that demonstrate 90% probability of detection and 95% confidence level for 0.05 inch flaw. This was mandated in the MIL A83444. And subsequently, there was a very big aircraft crash in 1988, that is the Aloha crash, where the entire top fuselage got blown away. Lost about 16 feet of pressure drop because of the flaw that was found there, caused by the multiple fatigue cracks. And luckily, only one person died. in that aircraft, and that opened up a big area of health monitoring in 1988, and substantial funding was put in US to actually in this area to address this health monitoring. So now coming back to aerospace, why do we need SHM for aerospace? I've given a number of different things, which is all, some of them are common sense, extended service cycles with reduced maintenance duration. That's one of the things. Replacement. So the idea of SHM is, if you take the NDE manual, they have tests they do periodically, whether they like it or not, after every flight, after every 10 flights, every 100 flights, and after 100 hours of flying, they bring this back to the aircraft hangar, they remove part by part, they examined it NDA through non-destructive inspection. This has to go, this is taking enormous toll on the flying of the aircraft, availability of the aircraft. Okay, and because of that, they want a method that replaces this periodical maintenance by condition-based maintenance. That is, you don't go to doctor every day morning to show your health. You go only when you feel sick. Like that, when the aircraft finds itself sick, it has to go, rather than every time you do a maintenance. And that is very much needed because aircrafts includes personal, and personal life is more important. And that is the reason why they have to do. So the SHM area started to actually see whether we can replace this periodical maintenance by condition-based maintenance. So, and that is one of the reasons why we need SHM for aerospace than any other disciplines. Then the monitored systems should exhibit longer operating life. And of course, today there are so many airlines that are going out of business. So most of them lease the vehicles, and the value of the aircraft will become high if you have a monitoring system in place. And that's one of the criteria now the aircrafts, the airline companies are insisting for, so that they have higher value for this one. And most importantly, today the SHM is, any aircraft is designed with a very high factor of safety. High factor of safety means more material. More material means more bulky. More bulky means less endurance and more consumes more fuel. It is less fuel efficient. So to move away from this, we need to introduce a new concept of design called SHM-based design. Okay. So basically, today we are all designing structures based on damage tolerant design. So they will say, we can tolerate this much amount of damage. That is specified. So it has to be monitored continuously to see that the damage doesn't exist for this the specified amount. So we need inspection for this one. But if you go to SHM-based technology, we can actually have leaner, less lighter weight, more endurance structures. More endurance means today we can fly from Bangalore to San Francisco without any stop. It should be able to tolerate. Today we don't, because we are always afraid of any damage coming there. So that is basically there. We are very far off, but at least now we are implementing damage tolerant design so that we can regularly monitor the aircraft after a certain number of flights. So these are the near-term and the long-term benefits. I have already talked about many of these things. Elimination of costly and potentially damaging structural disassembly. We don't have to do that. We need to have reducing inspection time. So that is where maintenance comes into picture. Minimize human factors. Many times the NDE people are so fatigued looking at each and every part. They actually miss out certain flaws when they do normal inspection. So we need to automate it, and SHM is a way to do that. Okay, and the long term is we need to have more design new philosophy, weight saving, and eventually move from schedule-based maintenance to condition-based maintenance. So now the question is, what is difference between non-destructive test or inspection and health monitoring? Health monitoring, non-destructive test is a subset of health monitoring, but they are not health monitoring by themselves. Why? So if you look at the definition, NDI is basically examination of a material to determine geometry, damage, or composition by using technology that does not affect its future usefulness. But it involves high degree of human interaction. And that is where the fatigue sets in. And it is very local and focused inspection on smaller areas, not on the global level, and require access to area of interest. And many times you don't have the access. Very, very difficult to get the access. However, SHM basically use smart concepts, and it needs NDI, but not in the local sense. It's in the goal is to, in the global sense, and the goal is to reduce the operational cost. And it has potential to actually automate this inspection process. So if you look at, so I'll come back to offline SHM. Why do we need it? This is a typical graph of a Boeing 737 aircraft. If you look at it, the inspection cost, the total inspection, 49% of the maintenance cost goes on inspection, just to see point by point. Okay. And the lower graph says how much each of the subsystems of the aircraft takes in inspection. Quite a few, you see, my objective is to reduce this 49% to say 15%. So that means I am reducing about 35% of the total maintenance. That means if you look at the commercial aircraft, they bring it to the hangar after every 100 flights. They remove part by part, inspect it, do NDI inspection, and assemble it back. So clearly about 15 days of time is lost. More than 15 days depending upon the size of the aircraft. For example, the Boeing A380 type bigger composite aircraft takes much more time. So if we can reduce by 35%, this will translate into billions of dollars to the aircraft industry. And that is where the SHM comes. It's very important. So there are the levels of SHM. So the first level is, there are 5 levels. And first level is whether there is a damage or not in the entire aircraft. Imagine a big aircraft. How can we say there is a damage first? That's the most difficult thing. And that is very small compared to the level 2. Once you find the damage, where it is found and what is the level? Is it very more or less? Where I can trigger certain maintenance activity at level 2 itself. And to trigger the maintenance at level 2, you need to know how severe the damage is. So we bring in the fracture mechanics concept. So is the stress is growing very fast? How fast it is going? And these are some of the things. Once that is there, I can say, okay, this is very small. Before it goes to the threshold value, which is given by the design specification, I can do some repair technology at the level 3. And after doing that, because it was designed at originally for certain amount of life, say about 20 years, and because of this damage, the life might come to about 18 or 17 years. So we need to find out how much the remaining damage life is there. So all these 4 levels, which are of increasing difficulty. The first itself is too difficult, and if you go on doing it, it becomes extremely difficult. And to do that, we need SHM technology. So this is the level of decrease that you are trying to handle it. So if we look at that from my introduction, the health monitoring comprises of 4 different areas. One is basically condition-based monitoring. In this condition-based monitoring, what will you measure to find out what is happening to the structure? You can measure voltage, you can measure current, you can measure velocities, you can measure temperature, pressure, name what it, and it depends on what structure and what is the operational condition. That is what are the parameters you're going to measure. And for this, you need novel NDE techniques. Many of them are well known, like strain gauge. Some of them use stat test. Some of them use eddy current probes. Some of them now, mostly people are using non-contact sensing. Without any wiring or something like that, can we bring in some new technologies, new sensor technologies, and corresponding NDE methodology. So there are various NDE methodologies that are in place, like laser Doppler hygrometer. I'm going to talk about it, piezo system, air-coupled ultrasonics, etc., etc. But all of this will not be sufficient unless we have very good modeling methods. And the modeling methods could be for different damage models. The damage scenario is different for metals, composite, or different kinds of structures at the macro level, micro level, and which requires extensive data. And then we need some new techniques based on the current scenario, like artificial intelligence, deep learning, machine learning techniques, new signal processing methods, etc. So all of this will form under the modeling method. So if you look at the whole health monitoring as an entity, it is a multidisciplinary assignment. It requires knowledge of mechanics, knowledge of mechanical engineering, knowledge of materials, knowledge of electronics, and knowledge of mathematics, signal processing. So it's a multidisciplinary entity if you really want to encompass all areas of health monitoring. So here I'm going to just talk about one area on sensor technology. This is only one small part of this big area, the big circle, and what are the things that we can actually do here. So what are the common flaws in metallic and composite? So in metals, we have cracks, holes, notches, and corrosion. Corrosion is very, very important. So we should be able to detect all of this. In composite, it's even more complex. You will have delamination between the two laminates. The fibers can break, the matrix can crush, and now you have new composite manufacturing methodology like co-cured, co-bonded structure, where the stiffener and the skin are manufactured together. And because of this manufacturing together, that becomes like a stress riser, and there will be D-bonds between skin and stiffener. And composites can absorb moisture and degrade, so the material properties degrade. And it happens not in all regions. In some region, we should be able to identify degradation. And some of them are periodic defects like rivet holes. There will be a series of rivet holes in aircraft, and these rivet holes will start when you bolt it. The corrosion will be occurring around, which will start actually deteriorating the structure. So all of these are very, very important. So if you look at it, typical, you have fatigue cracking, particularly at joints. Then you have corrosion. I said very important. You see the right-hand side here, how bad the corrosion around the riveted joint, which I talked about it. There may be a paint impact due to an impact event. Debonding, I have already told about it. And most importantly, impact damages. For example, even when the people are doing a regular maintenance, if there is a hammer that falls on a composite, there will be a div that is there, which will cause delamination. That is called BVID. BVID stands for barely visible impact damage. And that will create a lot of problems in maintenance. And some of the things I have already talked about it. So if you want to design a health monitoring system for detection of all these damages I talked about it, these are the criteria that are given based on certain mill standards, which I talked about there later before. That is, the design should be such a way that it should be able to detect 1 to 2 mm cracks in aluminum sheet, 5 mm cracks in metallic frame, or composites, delamination in composite, 100 mm crack in a large area, and when there is a corrosion, it will form pits, and the pitch, it should be able to detect 10% of the thickness. Pitch will eat the material, and it should be able to detect 10% of the material, thickness material. And in a co-bonded structure, it should be 15 into 15 mm of debonding should be able to do. And all of this, it should be repeatable, it should be so robust that you should have 90% reliability with 95% confidence level. Still, we are not on this kind of reliability on online health monitoring, but offline, we can realize these reliability very efficiently. So let's talk about in India, there are many programs. Our own LCA, which is mostly a composite aircraft. We have helicopter ALH manufactured from HAL, which is all composite helicopter. We have reusable launch vehicle from ISRO, which basically uses extensive composites where these SHM techniques are required. And many of the engines manufacturers have, the engine has both the hot section and the cold section, and more cold sections are basically made from composite, where all of this SHM technology is what I talked about is needed. So let's come to what are the different sensor technologies that is currently being used by aircraft industry. The major sensing principle. What is the sensing principle? So you trigger a signal, you acquire a signal. And from this, triggering and acquiring, you extract some signature. That is completely different from the healthy structure to a damaged structure. And using this signature, we will infer what is the state of the structure. That's a simple principle. And the response could be static or time dependent or dynamic. And the type of signature depends upon the type of structure on which SHM is mounted, operating environment, and environmental conditions. So what are the variables that you depend on? What are the variables you measure, and that depends upon the type of the structure and the type of SHM. You could monitor frequency, you can monitor wavelength, you can monitor voltage, you can monitor current, impedance, electrical resistance, vacuum pressure, strain gauges, Doppler shift, and so on and so forth, depend upon what kind of NDE equipment you use to actually measure it. Okay, so I will talk about a little bit of not all of them, but some of them here. So if you look at a typical monitoring techniques used in a different aircrafts, it depends upon what component you are monitoring and what is the material of the component that you are monitoring. For metals, if you want to monitor crack, you will look at these parameters: length, stress, strain, flight parameters, sound, vibrations. Where, especially for corrosion, you will monitor the thickness and also the sound, then vibration, chemical reaction. And these are some of the monitoring techniques. So you will have, some of them are visual, some of them are using strain gauge data, some of them using load sequence, acoustic emission, I'm going to talk about it, land waves, I'm going to talk about it, eddy current, ultrasonics. And these are some of the different ways that you monitor for different, and this is the damage detection technology, what you do. For example, crack, you change the observation and length measurement. So basically with visually you can find there is something going on. There are things like that. Some of the conventional sensors used in aircrafts are Freiberg rating. This is an optical sensor where that can be used as a sensor. I will come and talk about it a little later. Acoustic ultrasonics, comparative vacuum monitoring. This is a very useful method. Many of the aircrafts are using. Acoustic emission, some coatings, microwave sensors, imaging, eddy current, etc. So I'm not going to talk about everything, but I'm going to talk about something here and how it is used in the context of aircrafts. If you look at some of the sensor technology normally employed in typical aircraft, this is a slide taken from the Airbus. If you look at it, all this technology I mentioned in previous slide, like FBG, acoustic ultrasonic, CVM, etc. I've already given, I'll come back to the principles little later. What are the types they are monitoring? So FBG is mostly used to monitor loads, delamination, acousto-ultrasonics, delamination and cracks, a CVM for corrosion, etc., etc., etc. And if you see here on the last column, almost everything is offline. So that is, all of them are not taken when the aircraft is flying. When the aircraft is flying, they just monitor the loads. How do they monitor the loads? When the load levels increases, you will feel turbulence. You will, and that is all because there is a load monitoring system that basically says the level of turbulence that is there, and that is what the pilot announces you, and that is what is there. Except for online monitoring of loads, most of it is offline because still we haven't got the confidence level to monitor these defects online. So what are the conventional sensors? So one of the very useful sensors is comparative vacuum monitoring. It works on a very simple principle. So when the aircraft is manufactured, they do some theoretical analysis like finite element analysis, find the regions of very high stress for some design loads, and they put a vacuum system built into it at the time of manufacturing. So when the aircraft comes back to the hangar or to the terminal, so they connect this vacuum creation instrumentation and create a vacuum and monitor the pressure. If the pressure loss is not there, that means there is no crack. But the pressure difference is there, then you find that pressure difference creates, that is, vacuum is zero pressure. When I have zero pressure, no crack is there. But when the pressure is not zero, that means there is something happening in this area, and that requires a DE examination. And this is a very simple method. You don't need any time data or something like that. So you have an equipment, you measure the pressures due to vacuum, and if the pressure difference is large, then there is certainly a crack is detected there, and you need some remedial actions. And that's a very simple principle. And here is a simple way that it does there. So this is the configuration that happens, and when the crack is here, the pressure difference in these regions will not be zero, and there will be a loss of pressure that will be detected. Okay, so Airbus has used this technology extensively to monitor the crack. Where? So basically, for A380, it's a new skin made of composite. They use this technique for acceptance testing of this glass fiber aluminum composite, which is what is A380 is made of. Okay, and they could actually test this and certify it using this kind of a simple method. Very, very effective, very simple, but huge advantage to it to monitor very fast, rapid inspection when the aircraft comes to hangar. Of course, the difficulty is if you don't properly instrument this vacuum creation instrumentation at the time of manufacturing properly, then you will miss out on the regions where there would have been damages elsewhere. And that is something that you need to take care of. Okay. The second one is the acoustic emission. So it's basically like a lamp wave. Lamp wave is an ultrasonic wave that travels over a long distance without least attenuation. And what it does is whenever you trigger a lamp wave, you monitor the peak responses. And the peak responses are regions in certain areas. And then you can trigger it wherever you want, not at the location. You don't prior instrumentation. You can actually put a sensor when the aircraft comes to hangar and do it. But the problem here is the acoustic emission has the the instances of giving false alarm. That is, it can trigger panic even in the region when there is no damage. So it requires another method basically to actually verify the results you got from acoustic emission. That's one of the greatest disadvantage here. However, having said that, they have used this for a variety of applications. In Airbus A320, the fatigue test certification was done using acoustic emission. And during 1 year of damage, all damage detected by conventional NDT was also detected by AE system. That's what. You need to have another system to corroborate the results from AE. Furthermore, there are several damage sites were detected by AE before being found by conventional NDT. So this is a very robust method, but you need to work this method with another method to confirm the results from this method. The other one is the more latest one that is used is a PZT. PZT stands for, it's a PZT is a piezoelectric material. P stands for lead, zirconate, titanate. It's a material which can act like a sensors and actuator. So what this is a new technology made from Stanford by a group headed by Professor Fuko Chang. He has got a company called Acylin Technology. What they have made is, they made a fabric, patented product, where they have got this number of PZT sensors embedded into this fabric. So whichever the structure you want to monitor, you paste this fabric onto the structure so that it is firmly built into one over the another. And the advantage is, each of these sensor can be triggered as a sensor and you can measure it. So each one is done successively over a small region, and using a triangulation method, they find out the structural flaws. And many of the US Air Force and Navy people in US have used this technology now for flaw detection. It's been extremely popular, and they have come out with various new technologies to do this. But the fundamental thing is this new fabric they have put, which can bond on the structure, and then the bonding is so perfect that you can actually infer on what is happening to the structure based on the triangulation of the responses that are triggered from this piezo actuator. The next sensor is the fiber optic sensors. This is very useful in aircraft because you know that aircraft has a lot of electromagnetic interference, which will all the other sensors such as magnetic sensors, electric sensors are affected by this, so their efficiency will get reduced. This is very, very ideal in the aircraft situation because fiber optics is immune to electromagnetic interference. So how does it work? So before stating how does it work, it has a laser source which triggers a light wave. It has an optical sensor, it has a detector and signal processing. Based on this, you will find out what is happening in the path of the light propagation from here. The laser source will trigger a light wave. And if there is a crack here, the light wave is monitored. What is a parameter you monitor here? It is basically the wavelength. And change of the wavelength basically says there is something going on here. And that is a very simple concept that they use here. There are different types of fiber optic sensors, the point sensors, integrated sensors, quasi-distributed sensors. But most common thing about it is the point sensors based on what is called FBG, the fiber Bragg grating, and that's what I'll talk in the next slide. And that's very, very commonly used in aircraft applications. So what is this FBG sensors? So you have a optical fiber running through the structure. So you can actually embed that in a composite structure and you grate it. And each of these grating is a sensor. Okay. So what happens is when a light is passed through these sensors, it impacts this grating, and you measure the wavelength before the grating and after the grating. The change of wavelength basically says if there is a crack in this part, that there is going to be damaged. The idea here is you can multiplex it. So what they do multiplexing is they connect each of these grating through the entire structure so that one signal at one point, basically using this multiplexing, you can find out where is the damage surrounding each of these grating, and you can say at which grating, what point there is going to be a damage here. So essentially that is what is happening here. Okay, if the original wavelength is going to be plot is going to be a Gaussian pulse, and because of the interaction with the from the damage, you will see that completely change of the wavelength. So measuring that wavelength before and after, you should infer on what is happening to the crack in the structure. The other one is acousto-ultrasonics. This technique sends an acoustic wave into structure and intercepts them when they emerge from the other side of the damage. So you have one side of the damage, there are two sensors, one before and one after. It is like pitch catch mode. So you pitch it at one point and catch it at other point. If there is a deviation in the input signal, then you infer that there is going to be there. And some of these techniques are already, I told you that Airbus is using in their aircraft. Finally, the last sensor I'm going to talk about on general sensing is the eddy current sensor, which is mostly on surface and work on magnetostriction. So basically, the current passes through the magnetic circuits, changes the magnetic field. If there is a damage in the structure, on the surface of the structure. But the disadvantage here is this cannot monitor effectively if there is structure embedded inside the structure. For example, in the kind of laminate, you have a number of different lamina stacked together. If there is a if there is a delamination at say at the fifth interface, at the fifth laminate, you cannot monitor from the surface, mainly because the eddy current will not penetrate that high. But this was a technique that was used very successfully to monitor surface cracks. GE holds the major patent in this. They are the leaders in this technology. Most of the equipments that have come here is from GE. Okay. So till now we have said what is there, what are the different sensors that is used in the context of NDE. And I will go into now talk about what are the novel sensors we here in IISc have developed. We developed two different kinds of sensors. One is the magnetostrictive sensors. One is the laser Doppler vibrometer technique to actually monitor, and how we can do, I'll show you. So magnetostrictive sensors. So there are many magnetostrictive sensors. Here I'm going to talk about only one, which is called terphenol D. So terphenol comes from the name because it is made from a rare earth material called terbium, which is the rarest of the rare earth material, and an alloy of terbium, iron, and dysprosium with made, since it was first made in Naval Ordnance Lab, that is NOL, terphenol, NOL comes from there. And this has a chemical composition given here, TB 0.7, DY 0.73, FEX, where X takes the value 1.9 to 2, and depending upon what the value, the property of this alloy can change. The advantage is this comes both in powder form as well as in a thick rod form. The powder form is very useful because you can powder it, mix it with epoxy matrix. You can actually make a sensor embed into a composite. These sensors are both can be used for sensing as well as in actuation, and it will enable, as I said, to laminate construction. But it is very costly. How costly it is? 1 gram of terphenol is equal to 8 times the cost of gold. But that cost can be somewhat justified because it has large strengths. That means it can give large block force. The block force is I can generate because of actuation kilonewton of force. So initially when this material was made in Naval Ordnance Lab, it was thought of as an actuation material. It has narrow hysteresis loop compared to piezoelectric material, hence the loss is very low. However, it is weight heavy. It has stiffness as high as steel, 200 GPa, and it can come in lengths of 200 millimeters. So I have told advantage and disadvantage already. It requires very low voltage. It can be embedded. It can retain the magnetostrictive property both in bulk form and also in particle form. And the disadvantage is it has higher density, so heavy. It requires high current, low voltage, highly nonlinear, and it has, because of nonlinearity, it has double frequency effect, and of course it's very costly. So if you look at the constitutive model, the strain is related to stress and also the magnetic field. So D transpose H is called the Maxwell stress. This is coming from Maxwell's equation. This is the elasticity equation. The strain is related to stress as well as magnetic field, and the magnetic flux is related to stress, mechanical stress, and magnetic field through permeability. And here the compliance, the material property is measured at constant magnetic field.
Yes.
Yeah. And the magnetic field, the magnetic flux is related to this one, the constant strain, the permeability measured. So these are highly coupled. When you change H, basically as strain changes, when the strain changes, the stress changes. When the stress changes, the permeability changes. So you just cannot uncouple this equation. So that is where most people use uncoupled equation. When they uncouple it, they say that the magnetic field is directly proportional to current using the number of coils here. And this is a kind of a wrong assumption. Most of the work is done by this. You have to take these things together. Okay, so that is what is there. So these are the basically the if you look at the nonlinearity, how the nonlinearity comes, you see that for stress and strain, the constitutive model for different magnetic field, it is completely changing. It's highly nonlinear, so you cannot use the uncoupled field. So you have to come up with a new. Even the magnetostriction changes with different stress levels, and only manufacturers give you for certain things. If you want to design a sensor, we need to have a robust method to estimate it. So what we did here is we did a couple of numerical approach. We actually assumed the magnetostriction function of a polynomial function of magnetic field, and these constants were determined. So we took up to 12th order polynomial, and we determined based on the manufacturer data, so that for once I have this equation, whenever I feed any magnetic field, I should get magnetostriction. From magnetostriction, I will get the stress strain levels, I can get everything. And the second method is we created an artificial neural network where the stress levels given by manufacturer were fed, and the magnetostriction was determined as an output using a multi-layer network. And both of methods we have now done it, and we have actually got, so for any magnetic field, I can get the magnetostriction using these two approaches. And then we did a lot of numerical simulation to choose how good is our model. You see that the difference in the coupled and uncoupled approach, how the uncoupled approach gives erroneous results. And this is the damage detection algorithms we use when I use coupled and uncoupled, and we see that it is necessary to use coupled methods to actually get more reliable results. I'm not going to theoretical formulation of it. I want to keep the equation to the minimum, but I want to show that we have done this. So then we went to, once we actually got this model, we wanted to test it experimentally. So we bought this Teflon, the rods, we powdered it in inert atmosphere, we mixed with epoxy, we created a magnetophysical patch, and then embedded them in a 8 laminate composite. And then we induce the damages, and we want to find whether our method and my model gives exact results. So here the principle here is the magnetic field induced in the actuator patch will cause a stress in the sensor patch, and hence the open circuit voltage changes. If the open circuit voltage doesn't change, then there is no damage. If it changes, there indicates the presence of a delamination or a crack. And using this, we can quantify what is the level of damage that is there. So this is how we made it. Okay. So we took a 8-layer laminate, 8-ply laminate. Then we made a cutout for this patch in the laminate. So we fabricated the patch by mixing the epoxy with this, and then use magnet to pull this magnetostrictive material, and then took the leads out, put this patch in the middle of the laminate, and then fabricated it using our autoclave process. Once we do this, we have a magnetostrictive sensor embedded laminated composite. And this is the schematic. So we used a horseshoe system with a number of coils to induce the magnetic field, which passes into it. This is used as a actuator coil. This is used as a sensor coil. So we excite this using current, and the delamination is somewhere here using the open circuit voltage between the sensor and actuator. I should be able to find out where the damage is. And this is the experimental system. You have a signal generator, the ammeter to measure the current, power amplifier to amplify the voltage, the oscilloscope to see the responses. And this is the experiment, and this is the theory. When we trigger the signal, signal is a AC sine voltage, I equal to I naught sine omega t, where omega is varies from 100 to 400 hertz, and I naught varies from 1 milliampere to 4 milliamperes. And we were able to measure the voltage, and we were getting very good results between my numerical model, finite element model, and the experiments. So if you look at this is a video here, you could see the experimentally measured response on a laminate. Just 1 second. You can see when the laminate position is changing, the standard one, the black one, is the healthy one. But as the laminate size grows, you could see how the open circuit voltage changes. And based on it, we can actually find out whether the damage is there and where the damage is there. You could see for different levels of this one, the size of the damage. You can see for small size, at different, you have 1 delamination, 2 delamination, and all of these were captured experimentally. So the last topic I'm going to talk about it is the laser Doppler vibrometer. This is non-contact. All of this I talked is a contact sensing. So you need to have embedded these leads into the system, and the leads have to be connected externally to some system, NDI system, and measure certain quantities to infer what is going on. In this laser Doppler vibrometer, we don't have any contact. So we just shoot the laser, get the response, and find out what is going on. And that is very useful in the context of aerospace, because in an aircraft, you have kilometers of wires running all around the aircraft for monitoring many things. And we don't want to put one more thing there. So non-contact sensing is very useful in that respect. So what are the features? So whenever a small micron laser falls onto a vibrating structure, the Doppler shift happens, and Doppler shift is converted into time series of response, and that response is going to tell us what is going on. And that's a simple concept that we have used. So the advantage here is non-contact. You can measure what is going on to structure at least from 10 to 15 feet distance. and the laser beam spot size is less than 10 micron, and spatially dense measurement at micron size you can get. Signal distortion and damping due to bonded can be avoided. It can have grid spacing. You can monitor small regions, large regions. No disassembly, for example, in aircraft is needed. You can get the velocity components in all the three directions. Okay. So the principle is when a beam falls onto the vibrating structures, then the Doppler shift happens, and the Doppler shift is directly related to lambda, and this is converted into velocity time history, and that will give at every point pixel points that you have. So to see that, this is a vibrometer we have in our lab. This is the component. The distance is about 10 feet. This is a vibrating head. There is a data acquisition system here. So there is a PZT actuator is there, which will vibrate the structure, and the head will point out a laser here, and you have a laser camera here. So you choose the area where you want to monitor, and those area is pixelized. At each pixel point, you will get the response. So you have a seamless response all over, and you can use all the techniques you have to actually pinpoint where exactly you need. Okay, so this is the principle. So you have a function generator, you have a laser head, this is a piezoelectric, it points, and the complete wave field is measured. Okay, so this is the region I said. The camera chooses the region where you want to, and each region is pixelized. At every pixel points, I get it. So here is a T-pull joint, where it's a co-cued, co-bonded joint, where you have the skin and the stiffener. So I basically trigger this piezo actuator on the skin. Measurement I do in the skin, I infer based on the measurement what is happening on the stiffener here. So that is the area that I'm doing. And for example, in an area of 4.2 inches, I have so many pixel points, that is 45 pixel points. So I can get in a small area. So imagine I can even further pixelize much, much lower, depending upon my grid size. So this is a trigger. When I get this, when the laser falls here, the wave starts propagating, and I monitor this small region. Initially, wave comes here. This is at 50 seconds, 70 seconds, 90 seconds, 100 seconds, and 120 seconds. And there is the damage here in the square region marked. And you see that when it reaches here, completely it changes the wave pattern here. You could see. And clearly you can see that there is some damage here at the interface. You can clearly locate the damage very easily. I'll show you some more examples here. This is the coordinate system. I'm not going to go. This is the trigger signal that I can trigger through the PZT actuator. This is how this PZT is mounted. This is the 100 kilohertz excitation of this. So this is basically 100 kilohertz 5-cycle tone burst signal. And if you look at it, this is how it comes. You see, this is the flange wave interface at this time, and it interacts with the delamination at this point. And you can easily see there is mode coupling happening. It can be easily visible. This is taken from only one head. This is taken from 3 heads, 3 laser heads, and the delamination is much more clearly visible on the same pattern and the same sample. To demonstrate it more intensely, we have a very large aluminum plate. We made cuts here, different cuts. You see 0.03, 0.00625, 01, 0.025. And we chose to monitor only small regions close to this crack to see whether what this vibrometer gives. And this is the length of the crack, you can see. Okay, and if you see that, this is the video of the actual measurements taken at these 4 regions that was monitored. You could see here, when it hits the crack, suddenly you can see what is happening, very low. Here you see when the crack is there, more coupling is taking place here, but here the crack levels are so low, you can't see that, whereas you can see here. So here we need further algorithms based on this to find out. And we have developed a series of algorithms here. So if you see that, you could see the regions where I was using our RMS filtered response and damage index. We can actually figure out where the cracks is and what are their sizes very accurately. Then finally, we wanted to take it to the real aircraft. So we went to a Air Force base in US. This work was done in collaboration with Georgia Tech. So some of the algorithms were developed by me, instrumentation from there. And we actually, this is an F-18 aircraft that was done at regular maintenance. They gave us access to do this. So they gave us about 1 hour. We took this laser head there. We monitored the horizontal wing and the vertical wing. The way we monitored, this distance was about 7 feet. The piezo actuators were there. We acquired the data, we brought it back, and we actually see what is happening there. So this can be readily implemented. The idea I'm telling is this is not something of theoretical interest. This can really go into practice. So these are the overall test setup that we used. This is a vertical tail. These were the piezo actuators. It can be mounted on a laser tripod, and then we shot the laser here, vibrated the structure, we got the data. So if you look at this, this is on the horizontal tile, we can get the actual, this is a real-time data. So when the piezo tree goes there, I can get how the wave propagates, which is captured by non-contact. Absolutely no contact. There's only a contact is only for triggering the piezoelectric. So we could see something is going on in these regions. Something is going on in this region. And then we put this back and we put our own algorithms using these velocities, and we can actually get that. So this is on the vertical tile. We got this another video. You could see this is a lot more better. This is a lot more better, this one, using this. There is a clear wave propagation in vertical tile. And these are one things, and we have done this experiment on a very, very large number of samples, both in lab as well as in field. This is a honeycomb structure. This is a multi-layer composites. They are able to get the damage scenario. This is a composite lap joint. This is the metal rib of an aircraft. Okay, and where this region we had the damage, we could able figure out where exactly in this region was there. This is our GTRE blade, damage blade, where damage was 20 micron size. We could use this laser vibrometer technique to actually find out exactly where the damage is. This is the manufacturing defect. So every composite is immune to porosity. And if it is less than, more than 2% by volume, the pores, it is not aerospace grade. And we had a Boeing project, and we actually, they gave us a sample with different levels of porosity, and we used this technique to exactly find out where their high levels of porosity is there. And this is the wing spar attachment, where the damage scenario was the laser was put on the top surface, but the vibration was triggered in the other plane. And by monitoring this, the land wave will turn it and is able to give me the exact location of the damages. So there are several such examples that we have done. And now we have told the HAL. HAL is going to give us a big project on making one of the laser. Till today, we were using the laser Doppler vibrometer made from German company, which is very expensive. So we want to indigenize in India at least a fraction of the cost. So HAL is now convinced. They come back to us to actually use that. They're going to try this technology for them to be used. So this is my last slide. So in summary, we have used a number of sensors, CVM, that is comparative vacuum monitoring, and acoustic emission are only current sensors used by aerospace companies for SHM purpose. Fiber Bragg rating is a very good potential candidate for online SHM, and some of its implementation have already taken place in load monitoring. Terphenol D has a good potential to be a sensor material, and further developments in reducing the size of the sensor is necessary. Laser Doppler is a very good candidate for offline health monitoring. It can help to move from current practice of schedule-based maintenance to condition-based maintenance, because one person can do the monitoring of everything without disassembly. That is the great advantage. This alone can translate into millions of dollars to you. There are many new developments are taking place in the country. IIT Madras has a very good NDE department where they are making air-coupled ultrasonics, very useful because in the aircraft scenario, because most ultrasonics use water as couplant, now they come up with air as a couplant. It's very useful. Piezo array sensing, SMA sensors, CNT sensors. So this development is going on and on. Many people are doing it, and now more people are taking a lot of data is there. They don't know what to do, so developing machine learning algorithms to actually make sense of this data, reduce the number of data to only what is required, and this process of research is going at the next level now in health monitoring. So with this, I will stop. I can take questions. Thank you.
So the session is open for questions. Any question from the audience?
Either they didn't understand this, it looks like.
Well, sir, I have not understood many of the things because they are of very high level, I would say. Since you have taken us to the new heights, maybe the participants are a little bit hesitating to ask from you. Well, I will take the opportunity to get myself and ourselves enlightened by your lectures. I would say I just want to know that what thing is special in air-coupled ultrasonics? When we speak about ultrasonic testing, we say we need a couplant to transmit the ultrasonic wave into the material. But it's something special we are hearing from you, that air-coupled ultrasonics. So would you like to share your views in this regard?
See, regular ultrasonics normally has water as a couplant. So it is actually the equipment is immersed in the sample is immersed in the water, and then the ultrasonic waves is set up. Now, if it is air, if you have water, I cannot use this in aircraft scenario. So now they are moving away from water and they are coming up with air as a couplet. So there are two transducers which is held at certain distance from the equipment or the sample where you want to monitor, and sending out the signal through the air basically couples the air motion and the equipment motion so that I can get the responses. That is the same principle as ultrasonic. Instead of water, I have air. But the sensitivity of this response is much lower compared to water. Now that is being improved. Lot of improvements are taking place. So it's the same thing as ultrasonics, water ultrasonics, where water is used as couplet. Now we have air as a couplet.
So normally, what is the distance between the, I would say, transmitter and the object, the thickness of the air thickness,
Yeah.
what I would say?
Right. If it is very close, then the efficiency is very high. If it is very far, then the incident signal gets lost. So now they are now doing it a different way to actually using something called beam forming. So they beam it into a particular region where you want to do. So many hardware technologies is actually getting on. If you go to IIT Madras, Krishnan Balasubramanian's website, the NDE website, they have come up with a new design, and he has a company that markets this. It's called air coupled ultrasonics. So they have a special transducers to actually make the loss due to the incident signal much less. That is what it is.
So before we end, I have one more question, sir. I want to know that are we using this laser Doppler vibrometers? We are putting in the in the aircraft while the aircraft is flying, and we are able to sense it, or when the aircraft is grounded?
Only aircraft is grounded. We cannot put this when the aircraft is flying. This is only for offline health monitoring.
Offline. Okay. This was in your last slide over there.
Yeah.
So I think there are no more questions. I will take the opportunity to thank you. So we are highly thankful to you, sir, for enlightening all of us and taking us to the new heights of non-destructive testing. And I hope so your lecture had inspired all of us, and we will all continue to work hard in this very area. And time to time, some of our participants would be interacting with you, those who are working in the area of NDT of composites. That is an emerging area, and your lab at IISc Bangalore, Indian Institute of Sciences Bangalore, has already developed some lab setups. Maybe some of our candidates who are being recommended by head of the department would like to visit and do some work for their thesis work. So I hope so.
Absolutely. Any of them
who will entertain those research scholars.
Yeah, any of them who want me to get in touch with me, you can get in touch with me. Whatever little I can do, I will do. And when the pandemic gets over, yes, some of you, if you are visiting Bangalore, please do visit me. I can show you what we have done here. And of course, when the pandemic gets over, I would love to visit your campus.
Thank you, sir. Thank you, sir. Thanks a lot, sir.
Thank you.
Thank you, sir.
Thank you.
Professor Murslin, sir.
Ji, sir.
Should we start our feedback session? We will do valedictory session now. Just I think director has also joined, so we can start our valedictory session in another few minutes.
Okay, sir. Yeah.
Let's discuss with our director, Professor R. Sahgal, about his availability. Professor Murslin, sir.
Yes, sir.
Acha, that was just a glimpse of what the courses has happened. I was thinking that the director has joined the meeting, I would say. That was the glimpse of our activities.
Okay, no, let me call Shahid sir. Let me see whether he will be joining.
Okay. I did not notice that the glimpse of the screenshots of the meetings are going. So can we run it once again, Dr. H.S. Pali? Well,
Yes, sir. Yes, sir.
my dear participants,
I will run again. Okay. Okay. I
this
will.
is the just a glimpse of the activities which were conducted in our 5 days short-term course. Well, I will tell the shortcomings of this course a little bit. Our what was my experience that our practical session was not so clear, and the reason we found was that there were a lot of candidates who have joined, and that's why the clarity was not good. We have already done a Zoom meeting for practicals at INT Nardoni Institute of Non-Destructive Testing, where we have a very good clarity, and in future when we do online type of practicals, we will ensure that we make groups and we will have Zoom meeting over there so that we could get better clarity. I will share you the online practicals as a demo which were conducted at INT Nardoni Institute of Non-Destructive Testing, and you can see the clarity. I will share the videos. I would have uploaded them, but in my home the internet speed was not so good. I could not load them. So, but we'll be in touch. I would be sharing those videos, and this journey will not stop with this very short-term course. It will continue with we are planning to have practical sessions for non-destructive testing here at NIT Srinagar also, where we'll be shortlisting few candidates only, so that during Corona, this social distancing concept is being implemented, what we call that standard operating procedures, SOPs. Okay. So with these words, Professor Murslin has our Professor Shahid Salim has joined, our TQ coordinator, co-coordinator. See, wait. See this picture. This is the clarity over there. This is Nardoni himself using his torch to see the defect over there. See the clarity. This was in Zoom meeting. See the clarity. Only thing is that in Google Meet, when the participants are more, you cannot see. See the clarity of the piece which was being conducted over there, magnetic particle testing. This is also magnetic particle testing. So these were the snapshots of the videos of the practical session over there. So, Dr. H.S. Pali, what is your opinion about, we have taken the feedback you have sent to the participants, or what is this?
Yes, sir. We are collecting the feedback. Near about 30 responses we have, but it is requested to all. Please submit all. Requested to all participants. Please submit your valuable feedback. Otherwise, how can improve the quality of future programs?
Yes, we need your feedback. Another thing, what the students who have given the quiz, those would be evaluated, and we will be on the basis of that, we will be shortlisting the candidates for our online practical, not, I would say online, it would be offline, and we would be meeting physically with few students in group sessions for practical NDT testing here at NIT Srinagar. And also when we get the opportunity and we find anyone deserving and very much interested, we will make his way towards our branch office at Muscat and in INT Nardoni Institute, Italy, and also shortlisting them for our summer training program, where Nardoni himself may come here in Kashmir and train few students, maybe 2 or 3 or 5, because more students cannot be trained on some machines like phased array ultrasonics. Fine.
Okay,
So,
sir. So we
what
have
about our Professor Shai Salim? Has he joined?
sir. I think
He has joined. Well, sir, just check it. I told him. He told me I'm joining.
so. One announcement for the dear participants. You have to submit your valuable feedback, and after that we will share your certificate uh, on through the mail. Okay. So, is there any query regarding the your session attended during the last days? So you can see I have already shared the link in your WhatsApp group. Either you are comfortable in the WhatsApp group, it's okay. Otherwise, I will share these links with your mail also. So have you any doubt and any query regarding the up to these lectures? You can ask. Otherwise, uh, regarding the certificates, we will share the certificate very soon, within 3 or 4 days after the seeing your feedback responses.
Okay, we'll be also sharing some e-books after taking permission from Mohammed Murslin. He has shared some 2 good books on NDT also. E-books we'll be sharing with the participants also. And let me take permission from Nardoni. I have some books from American Society of Non-Destructive Testing, what he has shared with me. So if I could share, after taking permission from him, I would be sharing with some of the students on some specified topics only, not the whole book. Fine. So far as one of the student wanted to know information about acoustic emission testing material. So that also I am just looking to get the suitable information for him or her. So that's it.
Okay.
So
I sir,
Dr. Saifli has joined. So just Dr. Pali, just run the that 5-day glimpse for Professor Shai Salim if he has not seen it. If he has seen, then we will continue. He will.
No. Let's go ahead. Let's go ahead with the rest of this. I can see it later. Don't worry.
Okay. So Professor Murslin just introduced Professor Shai Salim.
Professor Shai Salim is a well-known faculty member of NIT Srinagar. There's no need to introduce him. He is known all over at least J&K. Without him, mechanical engineering department is incomplete.
Come on. That's a bit too much. Anyway, let's go ahead with the participants.
Let me add one more word, that he is the next aircraft of the mechanical engineering department, because he speaks very fast and tries to communicate the things very fast.
Yes.
This means he has a lot of huge quantum of information and knowledge with him. So may Almighty bless him more and more. And with these words, I would request Professor Shai Salim to just share his views for this very short-term course, and because he is our guest of honor in valedictory session.
Okay, thank you, Professor Sheikh Lamad. Thank you, Dr. Pali, Dr. Muslim. So 5 days, I don't know where they went off. It started on 26th, so it's already valedictory. So I just got a call, it's valedictory session. So you never know where 5 days has simply gone by. But at the same time, looking at the basically course structure that the department had envisaged and has been able to deliver during these past 5 days, on a really very important topic with the expertise of Sheikh Muhammad and the other experts from not only Italy, because they directly took you to be experts in this particular field and gave you, I think, the hands-on experience to all the participants, some of whom are our students as well. So they would have benefited quite a great deal from all of these interactions. Online is not easy to understand anything that is too technical, obviously, but you need to know the basics that are behind, whether you're looking at ultrasonic welding, whether you're looking at dye penetration testing, eddy current testing, phased array developments. And mostly because if you remember the first class which was taken by Professor Sheikh Ghulam, which was talking about the advances which have taken place in the non-destructive testing and evaluation over these years. The equipments that have evolved over a period of time, maybe somebody might have talked about the maintenance center that we have currently, which is now a CRFC center within the department, and the tribology lab is housed within it, plus IT department. It was envisaged with the government of Italy, with the government of India, to become as a maintenance center for catering to the maintenance needs of the entire region of the north within the country. But because of various issues, we were not able to come up to that level. But we remember still see the equipment that had been procured in the 1980s decade, and it was still at that time, even a decade after that, top of the line stuff. And then people did use it, and as Professor Sheikh Ghulam has used all of those equipments, a few of them, for his non-destructive testing and evaluation. So I feel that this particular course would have been of great interest and quite beneficial. In even a cursory glance at the course, and if you have got some of your basics, fundamentals, theory part, which you understood, and some of it which is related more to practical orientation, Professor Gopalakrishnan might have given you a good idea of where you have able to take these certifications, these courses. He has himself done some certain certification courses online as well as offline. So you could build up your resume as well as your these engineering skills in any direction you feel. You could go to CFD, you could go to additive manufacturing, you could go to NDT. A whole vista of knowledge is available to you, and all of these courses which have been designed by the Department of Mechanical Engineering during all of these tough times during the COVID pandemic have mostly provided the student community, the participants, with a whole vista of knowledge as to how they some fruitful knowledge, really practical knowledge in all of the areas of engineering and science. I wish, as well as congratulations to the mechanical engineering department, to the head of the department, Professor Sheikh Nazir Ahmed, who was basically the main driving force behind this course, motivating Dr. Muslim, Dr. Pali, and Dr. Sheikh Ghulam Ahmed in order to come up with this wonderful particular course. It was short, yes, that we can understand, but if it has given you a glimpse of it, of the fundamentals of NDT, I think that has been would have been a great challenge. And okay, congratulations to all of you. Thank you so much for having me on board today. Thank you.
Thank you, sir.
Thank you, sir, for the valuable words.
Thank you, sir. Thank you, Professor Shai Salim.
For your valuable and encouraging words.
Thank you, Professor. Thank you very much.
So, sir, any valuable feedback from the audience side or the participant side, please give.
So, the session is open for 1 or 2 minutes from the participants. At least 1 or 2 participants should speak something. They have given in written, but we want to hear also. If someone among you from the participants would like to share his experience related to this very online NDT course.
Come on, Zubair Alam, I think you are there. You can say something.
Yes, sir. Assalamu alaikum, sir.
Yes, I think this course must have been quite helpful for you. So can you share your experiences, please?
Yes, sir. मतलब ये बहुत ज़्यादा हमको encourage किया NDT बहुत ही ज़्यादा सर. मतलब पहले हम ये जानते ही नहीं थे कि मतलब ये एयरक्राफ्ट वगैरह का किस तरह से टेस्टिंग करते हैं. तो फिर अभी ऐसा लगता है कि मतलब ये बहुत बेनिफिशियल है. जैसे इंडस्ट्री वगैरह है तो उसमें अगर ये काम करते तो हमारे सोसाइटी के लिए बहुत ज़्यादा ही मतलब बेनिफिट होगा.
Yeah, thank you, Zubair. Okay, so anyone else? It's just basically your personal experiences, what you gained out of this course. So anybody else can talk about it.
Hello, sir.
Yes.
I'm Dr. Nusratullah.
Yeah, Dr. Nusratullah.
Yes, I first of all thank Sheikh Ghulam sir and organizers and NIT Srinagar for organizing this wonderful 5 days workshop, which was very useful for beginners as well as for those who are already expert in this field. The speakers were also very knowledgeable persons were there, like Anish Kumar, Dr. Anish Kumar and Dr. Nardoni and Gopalakrishnan from ISC. They have, their presentation was so good that it sparks us to think about this NDT and create interest in among all of us. Like they have, Dr. Anish Kumar has given very good lecture on ultrasonic, conventional and paper ultrasonic, where he explained like what is B scan, D scan, and C scan, like that. I was very inspired by this program and created a lot of interest on me. I thank
Okay, thank you, Dr.
Thank you, sir.
for
I think Paliji, Murshin sir, you can take it forward.
Yes, sir. Yes, sir. Thank you, sir. Thank you. Okay, sir. Sheikh sir, please wind up. I think it is requested again to participate. Please submit your feedback. Otherwise, without your feedback, it is very difficult to send to generate your participation certificate. So after your feedback, we will share your participation certificate.
And one thing,
Yes, I think since you have to all the participants, you have been there throughout this particular course. It's not all about participation certificates. Your feedback is important in the sense that what improvements can we make when we go for this course offline? Because obviously, hopefully, very soon we'll be ending up with this pandemic. It's taking time, but then everything changes. So maybe tomorrow we might have an offline course. Then we'll.
Yes, sir. Yes, sir. Exactly. Exactly.
So that way, your feedback would be important, and as soon as you submit that, I'm sure the organizers will be able to.
yes, sir.
Yes, sir. Exactly.
Shahid sir, Professor Shahid Salim, we intend to conduct an offline NDT course in the last week of November or first week of December, where we intend to give a training or certain equipments that are at NIT Srinagar like UT, MPT, extra. So that feedback will be essential.
Yes, sir. Actually, already we got the 40 responses from the participant side. Only, I think, near about 30 responses are remaining.
So I would just like to add, as a vote of thanks, just add what all those have been told by Professor Mohammad Mursaleen as vote of thanks. Just to add with, there was a team of Dr. H.S. Pali who was working behind this, organizing this very event for Google Meet, and the commander of the team was Dr. H.S. Pali. He, along with his 2 PhD scholars, managed to do all the links and your who was paying the fees, your details, your attendance, other things. So he was working behind the screen, and the person who was working behind the screen, he and his 2 PhD scholars, Mr. Ashish was also there, and the other person name I am not remembering.
Amit Kumar, sir. Amit Kumar.
Huh? Doctor?
Amit Kumar.
Abhijit.
Sir, Amit Kumar. Amit Kumar.
Amit Kumar and Ashish Kumar, they were working and they have done a wonderful job. Right from morning 8, they were working till the end of the session. So before your session and after your session also they were working, and also during the session. So we are highly grateful to them. Highly grateful. And all the team of Mechanical Engineering Department, NIT Srinagar, including professors, supporting staff, everyone.
Yes, sir. Without your support and support from the department members, faculty members, and staff, it is impossible to conduct the program. So thank you to all, sir.
Okay. So, Mursaleen, should we conclude now?
Yes, sir. But special thanks goes to Mr. Ishq Adam for making it possible for that offline train, those experiments from and Nadoni Institute, Italy.
Okay, thank you. That is his duty also.
No, it was not easy. It was very helpful
Yes,
for us.
otherwise it is very difficult, sir.
I'll again thank Professor Shahid Salim, Engineer Sheikh Ghulam Ahmad, Dr. H.S. Pali for their support. Thank you, sir. Thank you
Okay,
all.
thank you, sir. Thank you, sir. So, can I stop, sir, here?